You know, you probably walk past them every single day without a second thought.
Oh, absolutely.
I mean, think about the thick industrial piping running along the ceiling of a warehouse, or the residential gas lines tucked behind your neighborhood's water heaters, or even those massive commercial water mains hidden just on the other side of city drywall.
Yeah, you walk right past them.
Yeah,
We all do.
exactly. Completely unaware of the silent, electricity-free battles happening inside them at this very second.
It's wild because we look at a pipe and we just see a static metal tube.
Right.
But inside, there are massive physical forces continuously fluctuating. They're constantly threatening to overpressurize, spiral out of control, and just blow the system apart.
And the only thing keeping those fluid and gas systems from literally tearing themselves apart, or at the very least completely failing to do their jobs, are these ingenious, self-contained mechanical heroes.
Yeah, they really are heroes of modern infrastructure.
So today, for your deep dive, we are unpacking a highly detailed instructional manual used to train instrument technicians. Specifically, we are diving into a module on pressure regulators.
Which is such a fascinating topic.
It really is. Our mission here is to figure out how these purely mechanical devices balance sheer chaos and keep industrial systems perfectly regulated without a single microchip, sensor, or line of code.
And that independence is precisely why regulators are the absolute backbone of the industrial world.
Yeah.
I mean, they obtain the energy they need to operate directly from the fluid medium they are controlling.
So they don't even need to be plugged in.
No, not at all. They do not need an external power grid.
Right.
If the power plant goes down or the facility completely loses electricity, your mechanical pressure regulator does not care.
Wow.
Yeah, it just keeps working, leveraging the pressure of the system against itself.
Okay, let's unpack this. Because to understand how they weaponize that pressure,
Right.
we really need to look at the anatomy of this balance.
Right.
The manual breaks down every single pressure regulator into 3 essential elements.
Yeah, and no matter how complex the regulator looks on the outside, even those massive units you see in a refinery, it fundamentally relies on this triad of components.
Okay, so what's the first one?
First, you have the restricting element. Think of this as the physical gate.
Like a valve.
Exactly, like a single port globe valve or a butterfly valve.
Yeah.
Just something that can mechanically open and close to restrict the flow of the fluid.
Got it.
Second, you have the loading force. This is the muscle pushing against that restricting element to close it down.
Okay.
And third, you have the measuring element, which is typically this flexible rubber or metal diaphragm that actively senses the pressure in the system.
Wait, so is this basically like a bouncer at a crowded club?
Oh, I like that. How so?
Well, the restricting element is the door itself, opening and closing. The loading force is the bouncer's physical strength, trying to push the door shut to keep the club from getting over capacity.
Right, right.
And the measuring element is the bouncer's eyes, looking at the size of the crowd inside to know exactly when to push back against the door.
Yes. The bouncer analogy works perfectly for the basic intent. But if we look at the actual physics of the mechanism, it's a brilliant example of negative feedback in fluid dynamics.
Negative feedback, so the system corrects itself.
Exactly. The regulator's singular purpose is to put exactly as much gas into the downstream piping system as the equipment on the other end is taking out.
Just matching the demand.
Right. Let's trace the flow. If your system suddenly tries to put too much gas in, the downstream pressure, which engineers call P2, starts to increase.
And just to clarify for everyone listening, when we talk about P2 pushing against the diaphragm, the manual specifies we are dealing with gauge pressure, or TED.
That's an important distinction, yeah.
Right. We aren't talking about absolute pressure in a vacuum. The diaphragm is referencing the pressure of the gas relative to the ambient atmospheric pressure pushing on the outside of the regulator. It's sensing that exact differential.
And that differential is what drives the entire operation. That extra P2 pressure pushes up against the underside of the measuring diaphragm.
Pushing it like a balloon.
Yeah, exactly. As the diaphragm bulges upward from the excess pressure, it pushes against our downward loading force, compressing it.
Oh, I see.
Because everything is mechanically linked via a stem, compressing that downward force pulls the restricting valve closed.
So the flow is choked off.
Right. The downstream pressure drops back down, and mechanical balance is restored.
That is amazing. The problem literally solves itself using the energy of the problem.
It's elegant, right?
It really is. But since that loading force is what actually dictates how hard the valve gets pushed shut, we really need to understand how we apply that force.
Right, because the force isn't just magic.
Exactly. Looking at the history in the source material, early engineers just used gravity. Like, they used literal heavy iron weights.
Yeah, the earliest and simplest designs are weight-loaded regulators. You use a physical chunk of iron as the loading element, pressing down on the diaphragm to counterbalance the downstream P2 pressure pushing up.
That sounds clunky.
Oh, it was.
Huh.
The manual provides the baseline math for this, and it paints a stark picture of the physical limitations. Imagine you have a high-pressure upstream line coming in at 100 psig,
Okay, 100 in.
but your downstream equipment requires a regulated set point of exactly 10 psig.
So if your measuring diaphragm has an exposed surface area of, say, 10 square inches and you have 10 psig of gas pressure pushing up against it, well, force equals pressure times area.
Exactly.
So 10 times 10 means you have 100 pounds of upward pneumatic force acting on that diaphragm.
Which means to achieve equilibrium and keep that valve perfectly positioned, you have to balance a literal 100-pound iron weight on top of the regulator's diaphragm.
Wait, 100-pound weight just sitting there.
Just sitting there. The weight acts downward with 100 pounds of force, the gas pressure acts upward with 100 pounds of force, and the system hangs in perfect balance.
Wow.
And if the downstream pressure drops to 9 psig due to increased demand, the upward force is suddenly only 90 pounds.
So the weight wins.
Right. The 100-pound weight instantly wins the tug-of-war, pushing the valve open to let more gas in until the pressure hits 10 psig again.
If you're listening to this right now, I mean, just imagine being the technician tasked with adjusting the set point in a massive chemical plant.
Oh, it would be awful.
You'd have to climb a ladder carrying cast iron plates just to manually stack them on top of these valves every time the factory's flow demand changed.
And keep in mind, a 100-pound chunk of iron has massive inertia.
Oh, right. Because it's heavy.
Exactly. If the pressure spikes rapidly, that heavy weight is going to lag, bounce, and overshoot. It's an absolute nightmare to fine-tune.
So you can see why the industry abandoned weights and shifted to spring-loaded regulators?
Completely. Replacing a hunk of iron with a coiled spring revolutionized the industry.
How does that work mechanically?
By turning a threaded adjusting screw on top of the regulator housing, you physically compress the spring, which increases its downward kinetic force on the diaphragm.
Oh, that's much easier.
Yeah. A spring is defined by its spring rate, represented by the letter K. If a spring has a rate of 100 pounds per inch, compressing it exactly 1 inch generates 100 pounds of downward force.
And if you turn the screw to compress it 2 inches,
You get 200 pounds of force.
which means you just turn a wrench to dial in your set point instead of hitting the gym to lift iron plates.
Exactly. Much better for the technicians' backs.
But the manual points out that while springs solve the inertia and adjustability problems, they introduce a fundamental physical flaw into the system.
Yeah, they do.
It's a phenomenon called droop.
Droop, also known as offset. It's the unavoidable side effect of Hooke's law.
Okay, remind us what Hooke's law is.
Basically, the force a spring exerts is directly proportional to how much it is compressed. So when a factory turns on a massive bank of gas burners, the downstream demand spikes. The downstream P2 pressure drops from our 10 psig set point down to 9 psig.
Because they're using up the gas.
Exactly.
Yeah.
So the upward pneumatic force on the diaphragm drops to 90 pounds. Our tightly coiled spring overpowers the gas, extending downward to push the valve open and let more flow through.
But because the spring just extended downward to open the valve, it physically uncoiled.
Right.
It is now resting in a more relaxed state.
Yes, and that changes everything.
It's exactly like loading a pickup truck with a heavy payload, right?
Yeah.
If you drop a ton of bricks into the bed, the truck's suspension springs compress.
Yep.
If you take half the bricks out, the suspension rises, but it doesn't return to the original empty height. The mechanical travel of the suspension inherently changes its resting force.
That is the perfect way to visualize it. Because our regulator spring is now slightly more relaxed, it is no longer pushing down with its original 100 pounds of force.
Okay.
According to our 100 pound per inch spring rate, if the new equilibrium balances at 90 pounds of upward gas force, the spring must have extended by 0.1 inches.
So it is now only pushing down with 90 pounds of force.
Exactly. It fundamentally cannot push the pressure back up to the original 10 psig set point because it literally doesn't have the stored energy anymore.
That makes so much sense. So the wider the valve needs to open to meet high flow demand, the further the spring must relax.
And the lower the new stable pressure becomes.
The downstream pressure has drooped below your desired target.
And this mechanical trade-off appears at the other end of the spectrum as well, during a state called lockup.
Lockup. What's that?
Lockup is the extra surge of pressure above the set point required to shut the regulator off completely tight when downstream demand drops to absolute zero.
Like when the factory turns everything off for the night?
Yeah, exactly. If your valve disc is made of a soft elastomer seating against a sharp metal knife edge, the spring and the gas pressure have to fight each other just to force that soft disc deep enough into the metal edge to create a bubble-tight seal.
So we've established that the spring is great for adjustability, but it fights against perfect accuracy.
It's a compromise.
So if springs inherently cause this droop, how do engineers fight back without abandoning the convenience of springs altogether?
The initial fix is a mathematical manipulation of the spring rate itself. You just use a lighter spring.
Really? That's it.
Well, let's look at the math. If we swap our heavy 100-pound per inch spring for a much lighter one with a rate of 50 pounds per inch, we change the travel dynamics.
Okay.
To get our initial 100 pounds of downward force to match our 10-piece set point, we have to crank the adjusting screw down twice as far, compressing this lighter spring 2 whole inches instead of 1.
So it's wound up much tighter right out of the gate.
Exactly. When the downstream pressure drops to 9 sig, we need the spring to balance at 90 pounds of force.
With a 50-pound per inch spring, holding 90 pounds of force means it must be compressed 1.8 inches.
Right. It started at 2 inches and now it's at 1.8 inches. That means the spring extended and the valve opened by 0.2 inches.
Wow, notice the difference in capacity there. For the exact same 1 psi drop in downstream pressure, the lighter spring allowed the valve to open 0.2 inches. That's twice as far as the heavy spring.
Exactly. The regulator becomes highly sensitive, granting massively increased flow capacity with significantly less droop.
But wait, why not just use the lightest, most sensitive spring possible for everything to perfectly eliminate droop?
Because if you put a flimsy spring into a high-pressure industrial system, you lose all mechanical rigidity.
Oh, right.
The entire system suffers from instability. A tiny pressure wave hits the diaphragm, the light spring overreacts, the valve flies open, pressure spikes, the spring slams it shut.
So the regulator will just endlessly bounce and oscillate above and below the set point.
Yeah, it's called hunting. It's endlessly hunting for a balance it just can't hold.
Which forces manufacturers to carefully calculate the optimal spring rate, constantly trading off between capacity and stability.
It's always a balancing act. But mechanical engineering is rarely satisfied with a compromise.
And here's where it gets really interesting, because the manual details a way to fight droop that completely bypasses the spring.
Yeah, this is a brilliant fluid dynamics hack used in the Fisher 627 series regulator. They leverage a physical phenomenon called the vena contracta.
The vena contracta, that sounds intense.
It's a beautiful quirk of Bernoulli's principle. When a pressurized gas passes through a narrow restriction, like the orifice inside our regulator valve, the fluid streamlines converge, and it speeds up drastically.
It's like putting your thumb over the end of a garden hose, right?
Perfect analogy.
Yeah.
Yes. As the velocity of the gas increases, its kinetic energy spikes, which means its potential energy, its pressure, must proportionately decrease.
Okay, so speed goes up, pressure goes down.
Right. The exact point just downstream of the restriction where the fluid stream is at its absolute narrowest, its highest velocity, and its lowest pressure is the vena contracta.
And in a standard regulator, the measuring diaphragm senses the normal recovered downstream pressure further down the pipe where the gas is slowed back down.
Exactly. But the engineers behind the Fisher 627 series placed a pitot tube, which is a small, hollow sensing pipe, directly into the high-velocity slipstream of the vena contracta.
Okay.
And they route this artificially low pressure up to the measuring diaphragm instead of the true downstream pressure.
As downstream demand increases, the gas velocity shooting through the vena contracta accelerates rapidly, right?
Yes.
So the pressure localized at that exact point plummets, dropping much faster and much lower than the normal downstream pressure in the wider pipe.
You've got it.
Wait, I see what they're doing. By putting that pitot tube right at the vena contracta, they're intentionally feeding the diaphragm a false, artificially low pressure reading.
That is exactly what they're doing.
They're basically making the diaphragm panic so it opens the valve wider than it normally would.
Yes, it is a brilliant mechanical life hack. It physically amplifies the valve's reaction without having to rely on a flimsy spring.
That's genius.
It flattens out the performance curve and practically eliminates droop.
It's just an elegant manipulation of natural forces.
Mm-hmm.
And the manual pairs it with another mechanical hack found in the Fisher type HSR regulator, which is leverage.
Oh yeah, simple but incredibly effective.
Instead of the diaphragm pushing directly on the valve stem in a 1-to-1 ratio, the diaphragm pushes on a pivoting lever arm.
Right. This lever provides massive mechanical advantage, multiplying the diaphragm's force to provide high-powered shutoff capabilities when the valve needs to close tight against high inlet pressures.
So we've optimized the spring, we've tricked the physics with a pitot tube, and we've added levers.
Yep. We've pushed direct operation to its limits.
But what happens when you aren't regulating a 2-inch residential gas line, but say a massive 36-inch city main? I mean, you can't just build a 50-foot tall spring to handle that kind of flow volume.
No, you really can't. Direct operated regulators eventually hit a physical wall. When direct control fails to scale, you have to delegate.
Delegate.
Or bring in pilot-operated systems. When a massive industrial application requires absolute precision across huge swings in flow demand, a single regulator just cannot keep up.
So what do?
A pilot-operated system connects two independent regulators together to manage the load.
So what does this all mean? We are essentially building a Russian nesting doll of regulators, where a highly sensitive, tiny boss regulator tells a giant, heavy-duty worker regulator exactly what to do.
I love that analogy, yes. The smaller boss regulator is the pilot.
Okay.
Its sole purpose is to act as a pneumatic amplifier. Instead of the massive main diaphragm reacting to the downstream pressure directly, it reacts to a specific loading pressure that is fed to it by the pilot. The manual splits this manager-worker relationship into two distinct designs: loading systems and unloading systems.
Let's dig into the loading design first, which the manual refers to as two-path control, citing the Fisher 92B steam regulator and the 1098 EGR.
Right. In a loading design, the pilot explicitly adds or loads pressure onto the main diaphragm to force the main valve open against a heavy spring.
Okay, so why is it called two-path?
What makes it two-path is that the downstream P2 pressure is routed to both the pilot diaphragm and the main regulator diaphragm simultaneously.
Oh, both at the same time.
Yes, the main diaphragm feels the pressure drop immediately, providing a lightning-fast initial reaction.
Right.
But concurrently, the pilot senses that same drop, opens up, and channels high-pressure upstream gas through a fixed restriction tube, loading it onto the main diaphragm to push the massive valve wide open.
The internal bleed mechanics here are just fascinating. They are constantly bleeding pressure through that restriction to maintain a dynamic equilibrium.
Exactly. The pilot acts like a continuously variable transmission, infinitely adjusting the loading pressure to hold the main valve in the exact perfect position.
And because the pilot is doing all the hard analytical work, these two-path systems can limit droop to less than 1%, even when moving massive volumes of gas.
They are the absolute gold standard for high-capacity precision.
But I imagine that precision requires complex tubing and constant bleeding.
It does, which is why you contrast that with the unloading design, like the Fisher EZR.
Okay, how does unloading work?
In an unloading system, the default state of the massive main regulator is closed.
Okay.
The upstream high-pressure gas, P1, is continuously routed directly into the chamber above the main diaphragm.
So the upstream pressure is pushing down on it.
Yes, because the surface area on top of the diaphragm is larger than the flow area below it. This trapped upstream pressure naturally acts as an immense hydraulic clamp, forcing the main valve tightly shut.
The worker regulator is being held hostage by the pipeline's own pressure. So to open it, the pilot has to break that hold.
Yes. When downstream demand increases, the pilot valve opens and literally bleeds off or unloads that trapped P1 pressure from the top of the main diaphragm, venting it downstream faster than it can be refilled through the internal restriction.
Wow. Once that heavy clamping pressure is bled away, the raw upstream pressure pushing from below easily forces the main valve open.
You got it. Unloading systems are slightly slower to respond than two-path systems, but they are mechanically simpler, require fewer intricate components, and are highly economical for massive transmission lines.
This is all incredible engineering. But an observation struck me while reading through the final sections of the manual.
What's that?
Up until now, every single device we've talked about has been a pressure-reducing regulator. We are taking high pressure coming in and reducing it to a safe, steady level going out.
Right.
But constantly worrying about downstream demand assumes the supply coming in is infinite and perfectly stable.
Which is not always the case in the real world.
Exactly. What happens when the danger isn't a lack of supply, but the inlet pressure itself spiking completely out of control?
Well, then you have to invert the entire philosophy. You need the other half of the regulator family.
The back pressure regulators.
Yes. Back pressure regulators, like the Fisher MR108, and pressure relief valves, like the Fisher 63 EG.
Mechanically, looking at the cross sections in the manual, they look almost identical to the reducing regulators. I mean, they still have restricting, loading, and measuring
They
elements.
do, but their measuring element is piped to look upstream, not downstream.
Ah, so their purpose is entirely inverted.
Exactly. A back pressure regulator is designed to maintain a specific desired pressure upstream by varying the flow when the inlet gets too high.
Give us an example of that.
Think of a massive flare stack at a refinery. If the pressure inside the chemical process gets too high, the back pressure regulator opens up just enough to let that excess pressure escape into the flare header to be burned off.
So it's keeping the upstream process running at a perfect steady state.
Right, it's actively managing the flow to maintain upstream stability.
But what about a pressure relief valve? Even though it functions using the exact same mechanical physics, it's treated entirely differently by engineers, right?
It is. It isn't there to maintain flow. It's a pure safety device.
Right.
It sits entirely closed, doing absolutely nothing until the upstream pressure hits a critical danger point to the relief setting.
And then,
Then it pops wide open to dump the excess pressure and prevent the piping from catastrophically rupturing.
wow. So if we connect this to the bigger picture, the distinction between a back pressure regulator and a relief valve often comes down to pure engineering intent.
Yes, 100%. Are you installing this device to maintain a smooth, continuous upstream flow process, or are you installing it to stop a localized vessel from exploding?
The physical mechanics are largely the same. The application is what changes the name.
Exactly. And the manual notes that this same inverted logic applies to vacuum regulators too,
Yeah.
like the Fisher V695 VR.
Right, which use the same triad of components to manage negative pressure, pulling ambient air in only when a vacuum gets too deep. It is just wild to think about the evolution we've traced today.
So it's quite a journey.
We started this deep dive looking at a pipe with a 100-pound chunk of iron sitting on it, with technicians manually hauling weights up ladders.
Sounds exhausting just thinking about it.
It really does. And we followed the engineering journey to tuned coil springs, to hacking fluid dynamics by literally panicking the diaphragm with vena contracta pitot tubes, and finally to building Russian nesting doll pilot systems that utilize complex internal bleeding to achieve massive flow with less than 1% droop.
And they do it all operating entirely off the grid.
Completely off the grid. What's fascinating here is that it remains at its core just a marvel of applied physics.
Absolutely. These vast, sprawling industrial systems achieve plant-wide harmony using only the literal pressure of the problem they are trying to solve.
The chaos of the gas provides the exact kinetic energy needed to control the gas.
Yes. And, this raises an important question for us to mull over as we wrap up.
What's that?
In a world where we increasingly default to fragile digital algorithms, constant software updates, and highly vulnerable electrical grids to monitor and fix our systems, what modern problems are we severely over-engineering when a beautifully simple, self-contained mechanical negative feedback loop is all we really need?
That is a great question. And, the answer might just be hiding in plain sight, in those silent electricity-free battles happening inside the pipes you walk past every single day.